Okay, so section 8.1 starts by saying, gee, we've really got a lot of formulas now that we can use. These are them. And, you know, these are the ones that we've developed over the course of time. And now the question is, when you have a situation where you need to use one of these, do you recognize which one you need to use? And we also want to start to realize that we want to fit these things into a particular form. We want to use techniques such as use substitution, and there really are a wide variety of cases that we can deal with now. You know, we've gone from the case where, okay, if it's something where you can raise the power by 1 and divide by it, okay, so that's any polynomials, etc. But now we have a whole slew of different types we can do. So that formula page that I just showed you from the book, that's on page 448 of my book here. And, you know, it shows most of everything we talked about. I noticed that the ones that we most recently talked about, the inverse hyperbolic ones, they show the inverse sinh and inverse cosh, but they don't show inverse tangent and other ones like that. So there are a few more that we've actually talked about, but this is the vast majority of what we have. Now, sometimes they don't look like they fit into one of these categories, and you have to do some work in order to get there. One of the big ways that you tend to get into one of those forms would be by using trigonometric identities. So we all know, you know, we know basic, of course I'll start with a bad marker. And the basic idea that if we had secant squared x dx, and we know that that's one of the ones that comes right from those basic formulas, that's going to just be tangent. That just comes directly out of trig. So I'm not talking about cases like that. I'm talking about things that look more like this. I just continue to struggle with markers here. There we go. Secant x plus tangent x, quantity squared dx. Now, why is this a particular concern? Well, we look at this and we say, okay, we want to get this in a form that we can integrate all of them. And when I look at this, I say, well, this is a binomial. I am squaring it. This is a basic FOIL method. This is secant x plus tangent x times secant x plus tangent x. If I square that out, I'll get secant squared x. That'll be first times first, that thing squared. 2 times the product of those two. And finally, the last term squared. And all of that will be integrated with respect to x. Now, it's going to be integrated with respect to x. However, we also know that we can break this into 3 separate integrals. And if we break that into separate integrals, the first one becomes secant squared x dx. Now, because I'm going to break these into different integrals, I'm going to kind of put a little space in between them here and do that. That one is precisely, when you take the derivative of tangent, you get precisely secant. So therefore, this would integrate to tangent of x. And for that piece of the integral, we're done. What about over here? Well, over here, I would say, well, plus 2 times, and then I would have secant x tangent x dx. And again, breaking that into separate pieces, separating them out to deal with them separately. I look at secant x tangent x and say, well, the derivative of secant is precisely secant x tangent x. Therefore, that piece just integrates to secant. And of course, I still have the 2 sitting out front, and that's 2 secant x. So those two are very much, once we square this out, those two fit precisely into some form that's in that table. The last one, however, is more complicated. The last one, I said, well, then I've got the integral plus tangent squared x dx. Now, what's wrong with this? Well, we have tangent to a power. And tangent to a power, we don't raise the power by 1 and divide by it. We have to deal with what can I do with tangent squared of x? If it was secant squared, we know exactly what to do with it, but it's not secant squared. And so this is where I need to do something with tangent in order to rewrite it in a form that makes more sense. Now, in order to do this, we need to take advantage of trigonometric identities. And the most basic trig identities are these. Make sure that's within the picture that I'm seeing here. Yeah, that's what you can see. Okay, this, your basic sine squared plus cosine squared equals 1. That's unit circle of trig identity. That works, but also if you want the one that contains tangent and secant, so tangent squared would be sine squared over cosine squared. So if I take this whole thing and divide by cosine squared and look at it term by term, sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. So that's an identity. And we have tangent squared here. That means tangent squared would be secant squared minus 1. And so I rewrite this one. I can't immediately solve it like I did the other ones, but I can say, well, this will rewrite to secant squared x dx minus 1 dx, okay, based on the fact that if I subtract 1 from each side, I've got tangent squared x equals secant squared x minus 1. And I break that into two separate integrals. This one now, just like over here, secant squared is precisely tangent. And 1 integrates to just x. And so what I end up with, if I combine like terms here, tangent plus tangent is 2 tangent plus 2 secant minus 1, or minus x, rather. And that is the integral of this thing. So utilize that trig identity, and either divided by cosine squared gives you one that relates tangents and secants. Dividing by sine squared will give you one that will relate cotangents and cosecants. And you use that as a trig identity in order to take this to a place where you can't integrate.